Hi, I'm Paul Doan. I've seen way too many database-driven applications built which are brittle, rigid, and resistant to business change. I'm here to tell you there is another way, a better way, and to show you how. As we all know, software development practices and how we deliver new code incrementally to address evolving business needs are becoming far more fluid and agile. However, if we don't allow for agility in our live data to match the flexibility of these modern coding approaches, what we will build will still be resistant to change. So here let's explore the techniques to build optimal data-intensive applications that actually are evolvable yet still resilient. Before we explore these techniques, it's worth qualifying what I mean by shared data. And to do this, I have something I call the data access triangle, which really illustrates 3 different ways applications might access data. The first is shared data. Here you've got different applications using overlapping subsets of the same data in the same database. For example, you might have a bank that has an application for call center staff for accessing customer data. They may also have a mobile app for end users who are also accessing subsets of the same data. Separately, you've got isolated data. This is typically different microservices that each exclusively own their own subset of data. Here, if one microservice needs the data from another microservice, it won't access the data directly in the database. It will have to call the other microservice that owns that data to get the data back. The third is duplicated data. Now, you might be familiar with this from architectures like the event-driven architecture or command query responsibility segregation. Sometimes you might hear terms like database unbundled. In all these situations, what we're talking about here is copies of the data being distributed local to distinct different asynchronous services that each then operate on their own copy of the data. Now, whichever of these 3 approaches you're using, all 3 of them are equally supported and equally valid for use in MongoDB. Now, there isn't one single approach of all 3 that I could recommend in all situations. Unfortunately, like most things in life, there are trade-offs, and depending on your particular situation and requirements, you might find that the shared data approach is better, or the isolated data approach is better, or the duplicated data approach is better. I'm not going to go through all the pros and cons of each of these, but it's probably worth giving a couple of examples. So both the isolated data approach and the duplicated data approach have some common shared benefits. In both cases, they have their own version of data, and then that makes it easier for the code that uses that to evolve over time independently without too much forethought. However, that doesn't mean they don't come without drawbacks. Take the example of duplicated data. Because data is being copied, you've then got to make considerations around eventual consistency of that data, the actual fact that it has been duplicated, and the risks of divergence that are associated with that. In the isolated data approach, you might have different services owning different subsets of data, but if one service needs the data from the other service, it has to call that. It can't actually push down an optimal database call to the database using transactions and joins to bring together the data when that data set crosses boundaries between 2 services. And so there are potentially challenges around latency, for example. As I mentioned earlier, in this presentation, we're going to focus on the situation where there is a shared data set being used by multiple applications. The other 2 approaches are pretty well documented nowadays in the industry, but it is worth us looking again around the shared data approach, as we've identified there are some challenges around that about having different independent services evolving independently when they share the same data. So that's what we're going to dig into. It's worth making a quick note that in this presentation, I'm not going to distinguish between monoliths and microservices and the relative merits of each. The principles pretty much apply to all where there's a shared data set. Likewise, whenever I'm talking about pieces of code that evolve, I'm just going to refer to them as components. Now, in reality, in your situation, that could be different functions in the same application being added over time to deal with new requirements. It could be new libraries to deal with those new requirements. It could be new microservices being added. It could be new services being added. It could be new applications or a new set of applications. I'm not going to distinguish. I'm just going to talk about those as being components that need to evolve or be added to deal with business change. Okay, so what's the challenge we're talking about here? Let's say we're in an organization and we build a greenfield application, a component one here, and it goes live, successful, it's running in production, and there are consuming applications and services using that. That's got some set of data in the database. Then along comes a new business requirement requiring a second component that's actually going to use that same data set and that data model, but that needs some changes, some additions to the data model. Now, to perform those changes to the data model, that's going to affect component one. There's going to have to potentially be changes to that. So that means to add a second component, you've got to actually change an existing component as well. Likewise, a new business requirement comes along, component 3 comes along. Now, to introduce that and the additions that requires to the shared data model, that's going to require changes potentially to component 1 and component 2, just to be able to enable component 3 to come along and deliver its business requirements. And of course, all these components are running live in production. We don't really want downtime here. We want them to stay up. So as we go on over time, this problem is just going to compound and compound. By the time we get to the 20th new component, to make the data model changes to allow for that in the shared data set, that's going to require changes to 19 different components first of all. And so each time a new component's coming along, the time it takes to implement that requirement is just increasing because of that dependency matrix. Another way I can illustrate the problem is in this graph here. At the bottom, you can see the number of components increasing over time, and to the left, we're showing the relative time and cost to implement that component. As you can see here, what happens when there's a dependency between these components on the shared data set, if we're not cognizant of how we're evolving that data set, is that as the number of components increases, the time it takes and thus the cost to implement each new component is increased over time. What that really means is each time there's a new business requirement coming along, it's going to take longer and longer to respond to that business requirement and implement it until essentially the whole system grinds to the halt and prevents business growth. So some of you might be wondering, with something like MongoDB with its flexible data model, isn't that enough to provide the software agility required to respond to new business change? Well, no, it's not. It's a key foundation. You require the foundations of a flexible database model to support that, but it's also about the application processes on top and the practices. In the traditional relational database world, though, that foundation is almost impossible. Take, for example, responding to a business requirement that's going to require a data model change for some child table and a one-to-many relationship and have that added to the data model. Even with some of the versioning support in some newer versions of these traditional relational databases, they can't really cope with that type of change at the database level. So a flexible database model is key, but it's also about the practices on top. So how can we adopt a more flexible yet still robust approach? What we need is an approach that should apply regardless of programming language. So let's test it against the most strict and statically compiled language supported by MongoDB today, to be sure. So that programming language is Rust. If you're not familiar with Rust, Rust is a systems level programming language with a focus on speed, stability, and safety. It actually has stricter compile time checks than even C or C++. So from all appearances, it's going to be a very rigid, inflexible type programming language to use with something like MongoDB that has its flexible data model. Is there going to be resistance between the two? If we can prove the model and provide flexible, agile services that are built with Rust against MongoDB, then we could essentially prove it for any programming language. So that's what we'll dig into looking at Rust as our example. Also, it's worth looking at Rust because most of you out there are probably not familiar with Rust. So it's a good way to convey principles that apply to any programming language. You shouldn't need to know Rust to follow this presentation. So let's say we're holding a set of books in our database. Here's an example of one book. This is what it might look like if we were using the MongoDB command line tool, the shell, to connect to the database and look at one book record. We've got a book with a title, an author, year, and a quantity fields. If we now look at that in Rust, how that might be represented in Rust, pretty similar. We're using a struct in Rust, which is similar to, say, a struct in C or Go, or similar to a class in Java, C#, Python, or Ruby. And here again, that structure, that data structure in Rust has got some fields that we can see. 2 string fields and 2 integer fields. So what do we now do if we are in Rust code and we're using the MongoDB driver for Rust to talk to MongoDB, and we have an instance of that book, example book here in Rust, and we want to get that into MongoDB? Well, we'd use some code similar to maybe other programming languages that would actually extract that data from the native programming language structure or class, and get that into a BSON type format to be able to then send to the database, which is what we're doing here. So in the middle part here, we are constructing some BSON data with those fields, extracting the values from the original struct in Rust, and then the final line here, we're going to actually, on a collection in the MongoDB database we've connected to, we're going to actually insert that new BSON record. However, we also need to be cognizant that in the MongoDB database collection, a specific field might not appear in every document, and this point actually conveys information. Let's take an example. Let's say we have this book defined in Rust, and it's also got a field called explicit. That field is there to say whether the book contains explicit content or not. But perhaps that's optional. Perhaps that won't appear in every single book record in the database. And the fact that it doesn't appear in some book records actually implies that that book has not been reviewed yet to say whether it's sensitive or not. So there's actually almost three states to that field. If it doesn't exist, it means it's not been reviewed. If it does exist, it might be true or false. It might be explicit or not. And that's actually key information. MongoDB supports that, and we need to support that in our agile type solution. So the good news is that Rust actually has a well-used native concept to convey that the variable may have some value or no value. This is called an option in Rust. Let's see an example. So here we've modified this Rust structure, but now actually we're wrapping the value of each field in something called an option. And that's going to capture whether it's got a real value or it's a non-value. And you can see the example here for explicit. That can have actually three values. It could be marked as none, or it can be marked as true or false wrapped as some. So how do we support this optionality in code we are using to interact with the database? So here we can see again we're instantiating a book record in Rust, but this time the values of the struct fields are being wrapped in some or none. And so we can see here that the explicit field has actually got a non-value. It's not neither true nor false. It doesn't have a value. How can we then take that and insert that knowledge into the database as a new record? So here's some example code. In the first section here, we're basically in our code, we've decided to assume that there's always going to be a title, an author, a year, and a quantity. That's the business logic we've decided on. So in this case, we're using, don't worry about it too much, a function in Rust called unwrap that's basically going to take the value from the sum and just pull it straight out. So we're grabbing from the Rust structure the title, the author, the year, and the quantity, and we're adding it to this BSON document that we're starting to build out. Further down now, though, we're actually in our code thinking, oh, the explicit field may or may not exist. So we can actually test that. We're looking at the example book variable from struct, and we're looking at the explicit field, and we're saying only if it has a value, extract the value and add that as another BSON field called explicit. And then finally, we're getting the handle on the collection in MongoDB, the books collection, and we're asserting that new BSON record. Now, that BSON record that goes in may or may not have an explicit field now with it because of the logic we've used here. So that's how we're dealing with optionality when we're writing new records to the database. But what about when we're actually then going to query these records back out of the database and deal with optionality then? So here in this Rust example, we can see we've used the Rust driver to issue a find to the MongoDB collection, and we've got a set of records back, or a cursor pointing at a set of records. So we're then using a while loop to loop over each of these result records. And inside that loop, we're creating a result book struct in Rust, a new book structure, and we're setting the fields on that structure by extracting the values from the BSON document, the string value for title, the integer value for year, for example. But we know in our Rust structure, if we go back a couple of slides, we're actually wrapping these now in some or none. So essentially, we're using an extra function in Rust here, OK in this case, to essentially say, bring the title back, but include it, wrap it in a sum. And for explicit, what will happen when we use OK, it will say, bring the explicit value back, true or false, and wrap it in a sum. However, if that value doesn't exist, it will basically result in that field being a none rather than a true or false being wrapped in a sum. So that's how we're dealing with optionality coming back. And in our code, we can actually see when we're dealing with the Rust code with these books that, oh, the explicit field was none. So that's how we're honoring optional data coming back out of the database again. So this is good. We've now identified the first of our 6 resilient evolvability principles. This one, the first principle we found, is have the ability to support optional fields because field absence conveys meaning. But what if we want to use a document mapper tool in our code for convenience to serialize and deserialize data to and from the database, rather than writing all that logic to put data into the database and take it out like you saw just before? So if we wanted to do this in a relational type situation, we would use an object relational mapping tool. With document databases like MongoDB, there's something similar, typically called a document mapper. Now, some people may refer to these as an object document mapping tool, or ODM. That's fine. That's not always correct, though, because in some programming languages, there isn't even a concept of objects, but there are still data structures that can be supported by a document mapper to get the data out of that programming language and into MongoDB, or vice versa. There's some other key differences between ORMs in the relational world and document mappers. In an ORM world, the object relational mapping tool is translating object definitions in our programming language, Java, C#, Rust, whatever, and converting that into SQL to send to the database. It's also mapping each of those objects in the application to probably a set of normalized tables in the database generating joins. So it's a pretty heavyweight abstraction. It does a lot of work. Typically also it's inflexible. Whenever that data model changes, the ORM layer changes. That requires then all the different components that use it to be recompiled at the very least, if not changed. And so that dependency goes all the way up the stack. And whenever a change is being made to the data model, you've got to make changes all the way up the stack and affecting all the applications that use that. Now, obviously, we're striving for something different here with the database and the flexible data model and the practices on top. And typically, document mapper is a lot more lightweight, which helps here. Basically, a document mapper is typically mapping one data structure in your application, object or struct or whatever, to a single record, a single document in the database. It's a lot more lightweight as an abstraction. It's a thin layer. Now we need to determine, is that document mapper flexible enough for what we need here to provide this agility? When the data model changes, does it affect our document mapper layers that we've got already on all the existing components? That's what we're going to look at more. The other thing to bear in mind as well is not all document mappers are created equal. So just because we may or may not prove that a document mapper works well here for Rust, if you're looking at using these principles for a different programming language, let's say Java, JavaScript, whatever, and there are document mappers available for that, you're still going to have to analyze whether that document mapper supports some of the principles we've got here. So different programming languages will have different document mappers. Some programming languages will have generic mappers. There might be more than one type. Some of the programming languages might actually have MongoDB specific ones. In Rust, SERD is a generic Rust framework for efficiently serializing and deserializing Rust data structures to and from other formats. So it's effectively a document mapper, and we're going to look at using that. So to use that in Rust, it's pretty simple. Rust has a concept of being able to essentially tag structures and functions with attributes that the compiler can use to imply or infer additional behavior or meaning. So in this case, we can just mark our Rust structure representing a book to say it can be serialized and deserialized, and that will enable the SERD framework to be used to basically convert that book to and from other formats. And the SERD framework, which is generic to Rust, it's not MongoDB specific, that supports serializing from these Rust structures to JSON formats, Avro, YAML, Pickle, or BSON in our case. So to a BSON document or back from a BSON document. However, if we then go and use this SERD element to create a BSON document, we hit the problem we were trying to avoid before. It will actually come along and say, oh, I'm serializing this Rust object on the left with these 5 fields, including explicit that's marked none. And actually, what it inserts into the MongoDB database when we use the MongoDB driver with SERD is it will actually populate these fields, including the explicit field. And where that was marked as none in Rust, that will actually appear as a field in MongoDB, but it will have the value null. That's probably undesirable. As we saw before, we'd prefer probably to not have that field appear at all in MongoDB if it's none in Rust. So we've determined that using a document mapper is a problem here. Using SERD is a problem here. Well, actually, no, we haven't. Because SERD also lets us do something else. It actually lets us tag the attributes as well. And in this case, we can basically tell SERD to say, If that particular field is none, the option is none, don't actually serialize it. In our case, don't serialize it to be some. So what we get this time, once we've marked those fields on those fields in that structure to say skip if it's none, is we're now getting what we desire. When we go insert that Rust record on the left, and we've used Serde as the document mapper, and we've then inserted that into the MongoDB database, we can see that the explicit field is not appearing in the MongoDB database because it was marked as none in the structure. So that's exactly what we want. So document mappers can be very useful. They enable developers to write less code and hence be more productive. However, we should never let a document mapper prevent us from being able to use the power of in-place update operators when we need them. Let me give you an example. Let's say we have the library of books in our database, and we're actually holding a quantity field. How many of those books, in this case Earth Abides, how many of those we have in stock in the library at this point. So let's say we had one, and then let's say it was a really popular book and the library had asked for 12 more to appear. We might want to do some code that increments the quantity by 12, so hence it's 13, and to also track when that record was last modified. We can do that easily with MongoDB and the power of in-place updates. So we see an example on the left here in Rust code. There's two parts to this update. The first part is querying to find the exact book we want to update, where the title equals Earth Abides and the author equals George R. Stewart. And when we found that book, we're telling the database to apply these update operators to increment the quantity by 12 and to set the last modified value to the current time. These in-place update operators are a powerful and easy way to target changes. They don't have to take locks. They're intrinsically transactionally safe and thread safe. There's no race conditions going on. Maybe some other piece of code was trying to update the inventory at the same time. There's no issues there. That's all handled. So we want to be able to have the power of this in MongoDB. If we didn't have this power, we might actually start finding that updates coming in from one component could trample all over the updates of another component. So, use document mappers for finds and inserts by all means, but never for updates, because you will need the granularity and control to avoid overwriting and losing data written by other components. Okay, so we've now identified another resilient evolvability principle. This one is only use document mappers if they are not all or nothing, and only if they play nicely with the other 5 principles. So what we mean here is be careful not to choose a document mapper that, as well as being convenient for your queries, inserts and deletes, is actually forcing you to use it for your updates as well. And then you're not going to have the ability to do fine-grained updates against a particular set of documents in the database. Additionally, we've identified another resilient evolvability principle just now, and this is, for updates, always use in-place operators, changing targeted fields only. Replacing whole documents blows away changes made by other applications. So whether you're using a document mapper or not, you should be using in-place updates targeted to specific fields in the documents or database records that you want to update. Otherwise, you could lose the changes being made by other components that you don't know about, and some of the data they're setting you didn't even have awareness of, and you might blow them away. You need to avoid that. So let's just do a recap of what we've been doing here. So we've got, in this case, a Rust application using the MongoDB Rust driver to talk to the MongoDB database. And what we've done here with Rust is similar to what we might do with any other programming language and the respective MongoDB driver that's provided for that programming language. So here we were taking native Rust data in Rust data structures, and we showed examples of 2 different ways of getting that data out and getting that into a BSON document to give to the driver to send to the database, or to get the response back from the database from a find and get back into BSON to bring back to our Rust application. So we were showing where we actually wrote handwritten code to take fields out of a Rust structure and then put that into a new BSON document structure as fields before calling the Rust driver to do the CRUD operation. And we also showed using Serde, the document mapper in Rust, which would automatically translate a Rust structure into a BSON document that we could then give to the driver to send to the database or bring back out again. Now, in all these cases, we always had at least one line of code where our own code would take charge of using the driver to send the create command, the update command, the read command, or the delete command, regardless of whether we use the document mapper to convert Rust data into BSON data or back and forth, or whether we actually wrote code ourselves to do that. Now, this is an important factor because it gave us one of those key principles there. We were able for updates to be able to craft our own in-place update operators to send to the database and have control over that operation and not have to use a document mapper. I'm saying this because you need to be aware if you're using certain programming languages with certain document mappers that may be provided for that programming language to talk to MongoDB, or they may be more generic that you're using. Some of those may expect those document mappers to also take control of issuing the create, read, update, or delete command. And that's going to be problematic if we can't ourselves call the update command with our well-formed instructions to perform in-place updates. You're not going to be able to achieve that. So be aware of that. It's the sort of thing that if you're using an object relational mapping tool for a relational database, that ORM tool would take care of all that flow and control everything. We want more control of that as a developer ourselves rather than delegating all out to the mapper. So yeah, watch out for that one. Right, what if we add a new second component to meet a new business requirement which needs additions to the data model? So we've had some books data in here at the moment to deal with a specific component, but now a second component is going to come along. Our new component will manage third-party review scores of books in the library. So we had our existing book manager components to manage the inventory, how many books we had, what they were in the library. We're now adding an additional book review ratings component, which is going to take third-party reviews that might have been done out there by magazines or on some websites of the books, and we're actually going to capture those reviews and on what the score was. That's going to require some of the same data that was required by the existing book manager component, but it's actually going to need some different fields as well to do with scores. And you can see this here. So this second component is going to need some additions to the data model to represent books. Now, these scores required or being set and being used by the second component might not actually appear in all the records. Maybe some of the book records have never had any scores captured for them, but others have. So you're going to get that variability across the model as well as additions coming into the model for the second component. So again, how are we going to deal with that in Rust? Well, you can see on the left the first example component we had, and we've been using this so far. We had a Rust structure with 6 fields in that we wanted for that particular component. Now we're going to create a separate, completely different Rust component, a piece of code. It could be an application, a service, whatever. And that's going to have its own struct to represent a book. Now, there are some common fields in both here, but there's a different one here now, scores. The second component isn't interested in quantity, last modified, or explicit fields, but it's actually interested in a new field called scores, which actually happens to be, when represented in MongoDB, an array of subdocuments where each score has a reference to the third-party site and the rating that that third-party site gave. In Rust, we would represent that as a vector, and you can see how that's being represented here. So 2 components that have got different data structures to represent their data that are both going to be pointing at the same set of records in the database with overlapping concerns. So this is how you deal with it. The original component, if you follow the principles I'm showing here, shouldn't then change when the new component comes along and needs additive data model changes. So for the original component, each record that component has been inserting, it just creates a new document as you'd expect. It's the first time that document's going to exist. And that will only contain, that document, the fields that our first component knew about. In this case, it wouldn't have had scores in there. Scores didn't exist as a component at that point when the first component was created. For each record being queried by the original component should only be projecting back the fields that it cares about. Now, when that's the only component, the projecting back the fields it cares about are going to be no different than projecting back all the fields, because only one component has added one set of data at this point. But by doing that in that way up front, it means in the future, if there are additions to the data model, those new additions that this component didn't know about are not going to be projected back and breaking it. So that's key. And then thirdly, for this component, each time it performs an update, it should be using an in-place update, as we've talked about before, and it's only going to change the fields it cares about. For example, it might try and change quantity, last modified, author, title. but it won't be replacing the document completely during an update, because perhaps a new component has come along, like this second component, has now started recording scores against some existing book records. If this original component was then assuming for an update it could completely replace that document, it actually might blow away some of the scores data that came in from a subsequent new component. So those are the key principles. If you stick by those principles for each component you build, you will be able to have a system, a set of components that evolve over time that are tolerant of additive changes. And for each time a new component comes along that has some additions to the data model required, it shouldn't need changing all the existing components to be able to deal with that. They shouldn't break. Okay, so with this in place, we've established that no changes are required to the original component's code when the new component and its data model additions are onboarded. And we've also identified a new resilience evolvability principle, and that is, for finds, only ask for fields that are your concern. And this is to support variability and to reduce change dependency. This is especially important for dealing with additive data model changes like we've just discussed. Okay, that was additive changes. What happens though if we need to make mutative changes to the data model? For example, here's some examples here. Let's say for some reason, as the system evolves and all the different components evolve and applications evolve over time, and the data model's been running for a couple of years, let's say for some reason we need to change the quantity field and rename it to amount instead. Or maybe we were capturing the author as a single name of first name and last name and maybe middle name or initials originally, and now we actually want to have two separate fields, one for the first name and one for the last name in our data model. Or let's say we were just capturing for each book the last time it's been modified by a component, that date. And now actually we want to capture both the last time it's modified and who the person was that made that change, the editor, if you like. Or maybe even more complicated. Before we were just capturing one field to say when that book record was last modified, and now actually we want to accumulate a change history over time against each book, showing each time it was modified and who that person was that made that change, the editor, which could be an embedded array of subdocuments, or it could be an embedded array to a different collection that contains that change history. These are all examples, and there are others, of mutative changes which have varying degrees of impact, from very simple from the top to being quite complex down to the bottom. Before we look at how we might deal with some of those mutative data model changes in our components, it's worth just taking a step back and considering the typical data model change lifecycle for applications. Typically, when you're building a new system or a set of applications to deal with a brand new set of business requirements, as you move towards that 1.0 release, that minimal viable product, you're typically, as a developer, making lots of different data model changes. You're realizing you need some additional fields, and then you realized, actually, I should have captured those fields in a different way, or maybe pushed those fields down to a subdocument or into a different collection, for example. So you're getting lots of additive and mutative data model changes going on at once for that single component before its release. What tends to happen then, though, once that's gone live and that product, if you like, is still being owned over the months and years and dealing with new business requirements, each new business requirement tends to mostly drive additive data model changes to the data model. We had the example where we had adding a new business component to provide reviews for books. And in that case, that had additions to the data model for scores. And so most of these new requirements drive additive changes. By this time, the data model tends to have settled down, and there are less situations where you're thinking, oh, actually, we should have renamed this field like this or pushed it down to a subdocument. Those mutative changes tend to tail off and happen less and less often. So it's worth bearing in mind. We already have identified a process for dealing with additive changes which don't affect any existing components. What we're talking about here now is how we deal with the rarer, increasingly rarer mutative changes over time. How do we deal with that? So how are we going to deal with such mutative data model changes? Well, we use something I term the interim duplication approach. And for one or more releases, as we bring on new components, we're going to maintain these affected fields and pieces of data structure in the database in both the old format and duplicated into the new format. That allows us to get the new capabilities out to market quicker without having to necessarily change every single component that exists already. So there's a few rules of thumb to follow here. Any existing components that are performing inserts and updates will need to be refactored to now materialize those fields in both the old structure and the new structure together in the same record. What this means, though, is any existing read-only components, which will probably be the majority, can actually carry on and function unchanged using the old field structures that still exist. They don't know anything about the new structures and they don't care. We'll also go along and run a one-off database script that will go and modify any of the existing records in the database and duplicating the new structure in line to match the old structure's data but in the new format. Now this can be applied without having to take the database and the system down. The existing components carry on running throughout this process. They're not affected because they're only using the old versions or the old pieces of structure within the records they're reading. Then for the new business components, we just need to be cognizant of a couple of things. For the components performing the inserts or updates, like the existing components we had to change, they're also going to write and materialize the data within the records that is affected in both the old structure and the new structure. And then for the new records, the new components that are going to be read-only, they can just now read the structures in the new formats. And that means later on when we do want to actually remove the old structure, we're only also affecting certain components. So let's try and bring that to life a bit more. And why don't we dig into probably one of the more complex types of mutative changes we talked about before, where we had a single field at a top level in a document, and actually that's going to now change to be an array of sub-documents. So before we were tracking the last modified date for a document, for a record, now we're going to say we want to accumulate change history and record each time that record was changed with its date modified and who made that change, the editor. So let's look at the example code for this component, which is the component performing inserts or updates, which could be the same for the new component or the refactored existing component. Essentially, the in-place update that we're going to perform was shown an example of the Rust driver here on the left. It's going to duplicate the last modified data in both the old structure and the new structure shown on the right here without breaking existing read-only components. Here on the example on the left, we're capturing the timestamp, the current time for use for our update in a second. But the main body of this code on the left is performing an update of a single record. And the first part identifies that book record by title and author. And the second part is our instructions on how to change that existing record. And that's going to be in two parts. The first part is setting the value in the old structure, which is going to set the last modified field with the timestamp. The second part is going to push a new array element to an existing or new field called change history. If it doesn't already exist, it will create that field, and it will actually append the date modified with the timestamp as well and the name of the editor. So effectively on the right hand side here, you can see from this component, we've basically duplicated some data in both the old structure and the new structure. With this interim duplication approach, the need for wholesale changes is then removed from the critical path of getting new business capabilities out of the door quickly. To get that new business component built and delivered, we don't have to go and change every single existing component and have that hold up the release. What we have, though, is over time is some technical debt that is being accumulated that at some point we may want to address. But that doesn't have to be on that critical path for new business capabilities, and we can address those out of band in one go, where essentially we'll go back and refactor any code that may be referring to the old data structures within records, whether that's for reading or inserts or updates. You can think of this approach as actually an example of the common parallel change refactoring pattern, or some people may call it expand and contract. So essentially, for dealing with mutative changes, we can use the interim duplication approach, which is an example of the parallel change refactoring pattern. Therefore, by using the interim duplication approach, we reduce the blast radius of the rarer mutative change occurrences. We only need to change a few existing components, not all of them, to deal with this new business requirement. And what we've also done is identified another resilient evolvability principle. And this one is, for the rare data model mutative changes, adopt the interim duplication approach. This will reduce delaying high priority business requirements. So what about dealing with entity variance in the moment? In the real world, entities can vary and at times be treated similarly and at other times be treated differently. What do I mean by that? Let's give an example over the next few slides. So in this example, let's say we were a new e-commerce site selling paper books. And in our database, we might have some books records with the example shown on the left here, similar to what we've been talking about before. Now, on our e-commerce website, we might have various things going on, and that's shown by the three examples on the right here. We might, on the front page, have an area of the front page that's got a widget showing the top 10 selling books that current day on the e-commerce website. We'll probably also have a books website search bar, so you can search for books by anything, title, author, whatever, and see the results. We might also have a books ratings viewer web page where in part of the website you can go in and see all the ratings for those books and the scores and who made those ratings. Okay, so that business might launch, go live, that e-commerce site with those capabilities for paper books. And then over time, that e-commerce site becomes successful and the business sees the opportunity to expand and diversify. Actually, now they're going to start to want to provide audio books from the website for purchase as well, and electronic books as well. Now, there's a challenge there because audiobooks have some of the common fields as the paper books like title, author, and year, but they may have additional attributes like the duration of the audio or the quality of the audio. Electronic books, similarly, might have some of the common same attributes as paper books, but might have other unique attributes like text pop-ups. Can you actually click on a word and say, see the dictionary definition, for example? So if we're building this with entity variance in mind, we can do this in such a way where when we bring on audio books and electronic books with additional changes to the data model that might affect the data model, we don't have to go and change those existing parts of the website, those existing web widgets that are using book records. None of these need to change. So even if now some of the records they are reading are audio books or electronic books and not just paper books with attributes they didn't know about, they will still work. The top 10 selling books website widget will still show the top 10 selling books, even if some of those happen to be audio or electronic and it didn't even know about audio or electronic, because it isn't interested and isn't trying to use fields that are specific to those subcategories of books. At the same time, by bringing on these new types of variations of books, the website can then start to have other parts of the website that deal in specialities to do with, say, electronic books or audio books. So part of the website might have the ability to go and search for audiobooks specifically and allow you to listen to specific audiobooks. And they may be leveraging some of the new fields that have been introduced in audiobooks only that don't apply to paper or electronic books. Likewise, for the electronics books, there might be a specialist area to be able to look up those different types of books that might be using some of the new attributes. But essentially, by building that data model that can deal with entity variance, and we're bringing in new variations of these records over time, we don't necessarily break the existing components that don't care about the unique variations to those new elements. They're still seeing books regardless of whether paper, electronic, or audio, and still dealing with those fields that they know about and been able to provide the function they were built for. So we've built components that aren't brittle and don't break when things appear that don't concern them. And this brings in the last of our resilient evolvability principles that we're identifying, and that is to facilitate entity variance, because real-world entities do vary, especially when a business evolves and diversifies. Right, now it's time to wrap up and summarize the 6 principles we've identified. So what were those 6 principles? Well, 1. Support optional fields. 2. For finds, only ask for fields that are your concern. 3. For updates, always use in-place operators, changing targeted fields only. 4. For the rare data model mutative changes, adopt interim duplication. 5. Facilitate entity variance. And 6. Use document mappers if they are not all or nothing. Now, in this presentation, we've used Rust to bring these principles to life, but these principles apply equally whatever programming language you're using, whether that's C#, Java, Node.js, Python, whatever. At the end of the day, by adopting these principles, your software will enable varying structured data which embraces rather than inhibits real-world requirements. Your software won't break when additive data model changes occur to rapidly meet new business requirements. And you will have a process to deal with mutative data model changes, which reduces delays in delivering new business requirements. If you're interested in finding out more, I provide an example GitHub project online that provides 2 demo Rust applications using the library books example we've talked about in this presentation. And this gives examples of some of the principles in action, like record variability, field optionality, and gracefully dealing with additive data model changes. The link's shown below where you can find the application to have a look around. And that's it. Thanks for listening. And as I finish, I'd just like to thank Jake, Jay, and Mark for their valuable feedback that helped improve this presentation. You can check them out on Twitter.